Yes, please.
Shall I start?
Yes.
Okay. Heavenly Father, I thank you for the gift of life. Thank you for the gift of protection and everything that you have provided to us, King of Glory. As we are going into this lesson, request for your wisdom to understand whatever is going to be taught to us, King of Glory, such that we apply it where it's possible, Heavenly Father, King of Glory. Guide us, pay attention, Father Lord. Through Jesus Christ our Lord, Amen.
Amen. Thank you very much for that wonderful opening prayer. And I want to welcome you to our very second session. And this is our second lesson in this holiday. Last time, we were able to go through assessment guidelines, what to expect in a standard paper. And today, I felt it very important for us to look at physical equilibria 2. And in physical equilibria 2, of course, we are looking at chemistry. Someone was in the comment section asking whether it is history. We are on chemistry. And they're saying that in physical equilibria, these are some of the things that we have already tackled. There are those who have not yet finished all this, but I believe we can use this week and next week to complete everything that encompasses within the physical equilibria. So today I want us to look at ideal solutions and the deviations from ideal solutions. Then at the end of it all, we shall be looking at the azeotropes. Azeotropes. If you recall very well what an azeotrope is, you will be able to tell us. But of course, we may not finish everything in this session. The azeotropes will come in the next lesson. The reason of putting all this here is for you to go ahead and make research on the same. So it's a teacher, Nyinibibi Isaac, who will be taking us through today's session. And I expect today's session to be very interactive. Utilize the chat very well. And if you have any burning question, you raise up the hand so that we can be able to move together. Okay, now, what do I expect from us by end of this session? By end of this session, I expect us to have known a number of things. And number one, we should be able to explain what an ideal solution is. We should be able to apply Lord's law. We should also be able to distinguish between a positive and negative deviation. Then, these two are the ones we shall be able to look at in our next session. Number one, interpreting boiling point composition diagram, and also explaining the azeotrope formation. So these two are for our next lesson on Tuesday. But for today's session, I want us to maximize. If any questions comes from this area here about ideal solution, non-ideal solution, or what you call the real solutions, and then Laut's law, we are able to tackle that item with vigor and with energy. So those are the things that you are going to be looking at. Let me hope we are all ready with our books and some calculators, since we have some areas we shall be able to practice. Now, last time I told you that in the previous session, we were able to look at these constructs, then assessment objectives, and then the related topics. So, and these constructs are distributed in the paper. From each and every construct, there is an item that will be able to be set in our papers, in our mocks, in our UNEB this year, 2026. So that's the reason why I have to always come back and remind you that each and every topic you're studying is very important and is part of the accessible areas. Look at this. The assessment objective number 4. That's where we find the Equilibria 2, Equilibria 1, and then electrochemistry. So if we tackle this Equilibria 2 this holiday and we be sure that anything about Equilibria 2, we are very conversant. Then next time we can be able to look at electrochemistry. For Equilibria 1, we looked at it last time. We're able to see the Equilibria 1. And now this time round, let us talk about this, the Equilibria 2. Equilibria 2, we see how best we can maximize. Then in the same lesson, someone was asking, how do I know the topics under organic 1? How do I know the topics under organic 2? The topics under organic 3? So before we begin today's session, I want us to look at the syllabus for A level. And I'll be able to also share it in our chat so that we also have this document with us. Each and every time you're studying, when you're doing research, when you're going ahead of the teacher, you are able to know what you're remaining with, what you have already covered. Let me just display something here about just something small here about our syllabus for A level. It is here. Let me hope we are able to see it. Our syllabus for A level. If you can see it, please let me know in the chat that you can see the program planner. The program planner. Can I see those who are seeing it in the chat? Are we seeing that? Yeah, I can. Sheila is seeing it. Good. Good. Yes. No. Now Linda is saying has not yet. Angel has not yet. Please, if you have not yet, let me know. But you can check with your phone now, since very many learners have already seen. Now, can I have one person raise up the hand so that we can move together? I get to know that we are moving together. Just one person raise up the hand, and then you can unmute. Okay, good. Alinda, unmute. Alinda?
Yes, teacher. Yes,
Okay.
teacher.
I hope you can be able to see the program planner.
Yes.
Okay, so I want us to move together. When you look at this, here they are showing us what is supposed to be covered in Senior 5, Term 1. Then, the first topic is moles and equation. Now, when you look at moles and equation, under this topic, there are a number of subtopics that we have. Are you seeing that? So I believe you have already looked at this, you have finished this because this was for Senior 5 Term 1. Let me move on. When you come to the second topic, atomic and electronic structure, we have there 2 subtopics, which I believe you also completed very well. So your work is to go back and you do practice. Then bonding and structure is also part. And you recall very well that most these ones here, these ones are the ones we are looking at, which we have put in the other element of construct number 1. And they are all under the inorganic what? Chemistry. And then modes and equations, this one is under the physical, the branch of chemistry, the one we call the physical chemistry, the modes and equation. I'll be breaking it down slowly in that manner, so that when we go back to the other element of construct, you are able to see that. You can keep on. I know I'm going to give you this in the chat, but for revision purposes, you can still have this screenshot taken. Now for term 2, now we come to periodicity 1. Periodicity 1, still this is, inorganic chemistry, that's branch. And you can see what is covered in periodicity 1. Those who are asking now what is under periodicity 1, the periodic table, variation in trends and properties, trends in properties of group 2 elements, all those are under periodicity 1. Now when you come, we are here now. When you come to thermochemistry, this one is under which branch? Microphone, the one who is having microphone.
Yes, teacher.
Which branch do you find thermochemistry?
It is in physical.
In physical chemistry. We can see what is under thermochemistry. Enthalpy changes, types of enthalpies, and then the Born-Haber cycles and the lattice. And on that channel, the link I've given in the link, all these have been covered there. Thermochemistry is there, the Born-Haber cycles are there. So if you can have time and you go on that channel, and then you can be able to follow. Now, when you come, very nice. Someone was asking, which topics are under organic chemistry 1? So this is under, of course, organic chemistry. But under organic chemistry, we have 3 major topics: the organic 1, organic 2, and organic 3. Now, when you look at organic 1, it's where we have introduction to organic to organic compounds. And then we have the alkanes, and alkynes. So for those who are there in the previous lesson, I said in our lesson today, I'll be able to show us all this, and I believe we're able to see that very well. So that was supposed to be covered in term 2 of senior 5. Then, even these ones are still under organic 1. Look at this. We had organic 1, alkanes, alkynes, but it didn't end there. We continue also to see in term 3, we continue with organic 1, where we look at halogen or alkyl halides, halogen compounds, then the benzene and methyl benzene. So organic 1, there we say it is done. Then we come to Equilibria 1. Equilibria 1 is senior 5 term 3 work. So Equilibria 1, what is there in Equilibria 1? And I believe you have already seen it on the constructs. There is an item coming from either Equilibria 1, Equilibria 2, or thermo electrochemistry. Those are the 3 topics. So in one way or the other, there must be what? A question. So don't spot. Read each and everything and continue to practice. So the concept of chemical equilibria and chemical industry, ionic equilibria, hydrolysis. Now, hydrolysis of salts also, this topic has been covered very well on that link I shared in the chat. Those who have just joined, check on that chat. Then you check on that link. You go direct to the playlists. You'll be able to see hydrolysis of salts. It is there. Then solubility equilibria is here. Now, all these are under the branch of chemistry called what?
Physical teacher.
Yeah, it is also the physical chemistry. Okay, now that is senior 5. Senior 5, there we say bye to it. So if you have not yet covered any topic that you have mentioned so far, meaning you're still lacking behind, you're still in senior 5 work, but nevertheless, you have research books. You can still go back and you do research on those topics. There's a friend of ours who is in senior 5, but is almost finishing the syllabus. But now, as we're in senior 6, we have to make sure we go ahead. Even before the teacher finishes the syllabus, for you, you finish as early as possible. So that's why I'm going to give you this syllabus so to get to know. Senior 6. Now look at senior 6. There's someone who called me and was asking, is colligative property part of the new syllabus? I believe you can see. So in Equilibria 2, we have physical equilibria and colligative properties. And what I'm covering today is physical equilibria, which I believe today we are going to cover a lot from it. And then whatever remains, we shall cover it with colligative properties next week. So that we know for Equilibria 2, we are good. We are done. Now, that is still under physical chemistry, the branch physical chemistry. Then when you come to organic chemistry 2, that's where we find the alcohols, phenols. That's why we find the carbonyl compounds, that is the ketones and the aldehydes. And it's also where we find the carboxylic acid. And still, this is under the branch of chemistry called organic chem. Now, for these, I expect us to have covered. But even if you have not covered all of them, there's no problem. You can do research and make your own notes. The good thing, this syllabus book, it tells you what you're supposed to research about so that you don't research too much, even for university. So for university, leave it out. The good thing, this one will guide you on where to read and how to utilize. Now, when you come to term 2, that's where we shall find the electrochemistry. That's why we shall find periodicity 2. Now, periodicity 2, that is under inorganic chem. Then electrochemistry is still under the
Chemistry.
physical chemistry. So electrochemistry, Equilibria 1 and Equilibrium 2. These three topics, they are making a full element of construct. So electrochemistry, Equilibria 1, Equilibria 2, those are the three topics that make up an element of construct. Then periodicity 2, periodicity 1, and then the other first two topics, the electronic structure and bonding. Those ones, they make another element of what? Construct about inorganic chemistry. So I'm letting you know about this that we can go ahead and read about all these things. The last one is just, there are only two. These ones don't wait for term 3 senior 6. Read them in this term. When you come back in the next term holiday, I expect us to have finished all these organic theory and reaction kinetics. These ones. Read about them. Go ahead, read about them. The good thing, they're not very hard. If you have studied chapter 3, chemical reaction rates of senior 3, then this one becomes very easy. What they are adding is just order of reaction. But these other ones, you already know them. The factors affecting rates of reaction, you already know them. But now this time round, we were seeing how do we determine the order of reaction. So let's go ahead, read all of these things, get a textbook. I'll be able to share with you some of the textbooks having these notes so that we can go ahead of the teacher. Our work is to guide you, and you go ahead and make notes. If you get any issue, ask the teacher to guide you. That marks the end of what I wanted to share with you in the syllabus. Let's now go ahead and we continue from where we had stopped. Okay, let's just continue from there. We're just here, the constructs. So from what we have seen right now, I believe when you see organic 1, organic 2, organic 3, we are sure about which subtopics are present there. But these are the bigger topics, which are make the element of construct or assessment objective number 2 under this construct. Then the ones for inorganic chem is all in element of construct number 1 or assessment objective 1. And we can see all of them, they are here. The good thing you've already seen which subtopics are present in periodicity 1, the ones in periodicity 2. Then stoichiometry in assessment objective 3, where we have moles and equations. You saw that. Thermochemistry, reaction kinetics. Then the one we are looking at today, Equilibria 2, is right here. Equilibria 2, Equilibria 1, and electrochemistry. If you want to see how these elements of construct, all these constructs are distributed in the standard paper, let's revisit our video we shared in the previous lesson, and then you can be able to follow. But for now, allow me dive into our topic, Equilibria 2. And as we look at this topic, Equilibria 2, I would like us to first understand what Laut's law is, because Laut's law will help us to understand what an ideal solution is and what a non-ideal solution is. Who can state for us Laut's law by show of hands? The one with the microphone, are you able to give us a hint about Laut's law?
Another person.
Okay, another person. Lydia. Yes, Lydia? Yes, Lydia.
Yes, teacher.
Mm-hmm.
Raoult's law states that
Mm.
the vapor pressure of pure components
Mm.
is equal to the vapor pressure. No, sorry, teacher.
Uh-huh.
The partial pressure of a component
Mm.
is equal to the vapor pressure of pure component multiplied by its mole fraction.
Oh, so I can just summarize it by telling us that partial vapor pressure of a component. Maybe let's say this component is A, is equal
Yes.
to
P,
P
it's not
in pure state. Okay, good. Times what?
times XA,
What is XA?
mole fraction.
The mole fraction. Very good. Can we clap hands for Lydia? Lydia, thank you. So Lydia has already given us what Lord's law of partial vapor pressure is. That it says that the partial vapor pressure of a component in a dilute solution is equal to the product of the vapor pressure of a pure of the component in its pure state times the mole fraction. And that is what you call the Lao-Tzu law. Maybe if I can just put for us the one I have here. This states that the partial vapor pressure of a component in a dilute or ideal solution is equal to the product of the mole fraction of component in the mixture and its vapor pressure when pure, mole fraction of component in the mixture and its vapor pressure when pure at a constant temperature. It should be at a constant temperature. And we have already said that it can be summarized like that. We are saying that the partial vapor pressure of a component equal to the product. So this can summarize it like that, the way they have already given it to us. And in that, we are saying that where the PA is the partial vapor pressure of the component A in the mixture, and then P naught A is vapor pressure of component A when pure, in its pure state. And finally, XA is the mole fraction of component in the mixture. So that is what Laut's law is. But if you look at our law, we are saying of the component in a dilute or ideal solution. So there are two. You can use the dilute or in ideal solution, which is still okay. But now the question is, what is this ideal solution? Don't forget, our learning objectives today, if you look at our learning objectives, we should be able to understand what an ideal solution is, and then we apply the Laut's what? Law. We have already understood what Laut's law is, but we need to understand what is an ideal what? Solution. Then after that, we see those which deviate from the ideal solution positively and those which deviate negatively. So I expect us to participate very much here. Right here, there is a question for us. What is an ideal solution? And then look at the second question. State the characteristics of an ideal solution, and you give some examples of ideal solutions. I'm going to first pause and I get responses, both in the chat and by show of hands. Let me see in the chat. Please, let's try. What is an ideal solution? Because if you don't know what it is, then you can't explain it. So that's why we need to know what it is. Johnny Paul. Johnny Paul, you can unmute as others are putting their responses.
So, good afternoon, teacher.
Good afternoon.
So, an ideal solution is a solution where the cohesive forces and the adhesional forces are equal, and the solutions are formed with no change in volume or heat and follows Laut's law So
I didn't get you.
That's my idea.
Okay, I want to
You
note
didn't
down
get
what
me.
you have. I didn't get you clearly. What did you say?
Okay, an ideal solution is the solution whose cohesive and adhesive forces are equal and are formed with no change in heat or volume and also follows Laut's law.
One also follows the
Laut's
Lao-Tzu law. Okay,
law.
good. Thank you. So at least you have given us that that solution whose cohesive and adhesive forces are equal. Another key point I have seen that it follows the Lao-Tzu law. Very good. Let me also see in the chat someone is saying an ideal solution is the solution in which the forces of cohesion and adhesion are equal, formed with no change in heat and volume and obeys Lord's law. Very nice. I think those are very nice submissions. We all know what an ideal solution is. So what are some of the characteristics? What are some of the characteristics of Lao-Tzu, of an ideal solution? We can give only 4 characteristics. Let's put in the chat. Let's put in the chat characteristics. Okay, I haven't seen any. Maybe let me have Shadia. Yes, Shadia.
Yes, good afternoon, sir.
Good afternoon.
So some of the characteristics, one of them is that the volume of the solution is equal to the sum of the volumes of the pure components making the solution,
Is equal
whereby
to?
it is equal to the sum of the volumes of the pure components making the solution.
Okay.
Then
So
the
you're
second
saying,
one,
the second,
no heat change occurs on mixing.
no heat change occurs on mixing.
Yes.
Thank you, thank you. Thank you, Shadia. Can we have also another person who can add the remaining 2 points? Thank you, Shadia. Can we clap hands for Shadia? Let's clap hands for her. Thank you very much. Let me have another person also. Okay, thank you. Who else can take us through the remaining 2 points? And then another one who will give us some examples. Some examples, like only, even if there are 3 examples. Who is ready to give us more other characteristics? Yes, Praise. Praise has gone. Okay. Okay. Yes, Sky? Skylar?
The other one says the cohesive and adhesive forces are equal.
The cohesive and adhesive forces are equal. Okay, another one.
The total volume of an ideal solution is the sum of the volumes of the components that form the ideal solution.
That one was the first one. Now I want the 4th. Okay, I'm seeing Sharon is already putting examples. Thank you. What and that. Okay, now, could you give us another, at least 2 examples? Kayondo.
Yes,
Thank you.
Master.
An example of.
They obey. Another characteristic is that they obey Raoult's law.
They obey
Raoult's
law.
Yes.
Okay, what about an example? Give me one example.
An example. Hey, master. We have benzene and methylbenzene.
It's saying benzene and methylbenzene. Benzene.
We also have hexane and heptane.
Then you have heptane.
We have hexane and heptane.
Okay, heptane and hexane,
Chlor
or we can even
chloro
have the octane.
chlorobenzene and methylbenzene.
Okay, thank you, Kayondo. Thank you very much for your submission. At least I can see that
Okay,
we
master.
all have a clue if we come to an ideal solution, and then stating the characteristics and giving some examples. Maybe if we can move on here, you see when you talk about an ideal solution, like you have already shared with us, it is the one that obeys Laut's law at all conditions of temperature and pressure. So that solution that obeys the Laut's law at all conditions is the one you're calling the ideal solution. But also, it is the one where the intermolecular forces of attraction between the particles of individual pure components and the particles of different components in the mixture are similar or uniform. That is the one which also gives us the other one, the cohesion and adhesion. Okay, there is no change even in the heat. So those are some of the characteristics that they have given us that rhyme with this statement, where we're saying that the intermolecular force between the particles of individual, if you have component A and B, so intermolecular force of attraction between the individual components A and B, and also the intermolecular force of attraction between the particles between AB in the mixture, they are similar or they have a uniform strength. But there's another point that we have here, that when such mixtures is being formed, when such a mixture is being formed, there is no heat what? Change. And the volume of the mixture is equal to the sum of volumes of individual components making up the mixture. I believe these are the points that most of you have already given us, showing us the different characteristics of what an ideal solution is. So we have been able to describe an ideal solution very, very well. So thank you. And I believe when we look at now here, we have the ideal solution, the characteristic. When we look at the characteristics of ideal solution like we have already shared, number one, we say that they obey Lord's law at all concentrations or at all conditions. The intermolecular forces of forces between unlike molecules are nearly equal to those between the like molecules. They are giving us like the intermolecular forces of attraction between AA and BB are approximately equal to the one for A and B. That is just an example. Then there's no heat change during the mixing. Then there is no volume change on the mixing. Then, which means if you have 40 of A, 40 of B, the total becomes 80. There's no change in the volume. The total volume is equal to the sum of the individual volumes. Then components mix uniformly in all proportions. And finally, the vapor pressure varies nearly with the composition. The vapor pressure varies linearly with composition. This is going to help us even when we are looking at the diagrams of which are representing the ideal solution, where we're saying that the vapor pressure is varying nearly with the composition. Now, when we have already given the examples of ideal solution and we say that we can have maybe let me first put the one they have already given us. They gave us the one for benzene. Okay, benzene and taurine, or someone saying that benzene and methyl benzene and methyl benzene. I'm just using the ones that you guys gave me. Then there's one who gave me hexane and heptane. That was already mentioned. Chlorobenzene and bromobenzene. It was already mentioned. Maybe we have also this one, propane. Propan 1-ol, propan 1-ol, and propan 2-ol, and propan 2-ol. This is propan 1-ol and propan 2-ol plus all this. So you can see we have a number of examples when you talk about the ideal solutions. Someone, Kayondo, do you have a question? I want us to move on.
Yes, Master. Sorry
Yes,
to take
please.
you back. Can I define an ideal gas as a solution? Can I define an ideal gas as a solution whose cohesion and adhesion forces are equal with no change in heat or volume and obeys Raoult's law at a given temperature?
Are you defining ideal gas or ideal solution?
Ideal solution.
Okay. So if I thought you were confusing between an ideal gas and ideal solution. So in this case, we are
No.
looking at ideal solution. And if you give that definition of yours, it is very correct because it encompasses
Yes.
these characteristics. Are you seeing that? So your answer remains
Yes.
very correct. Your answer is very correct.
Correct. Okay.
But of course, there's no one day when they're going to come and ask you what is an ideal solution. But we shall be applying these concepts in solving real life sort of questions, problems. You get? But you can't solve a problem when you have not understood what the problem is. That's why I want us to understand what an ideal solution is, its characteristics, where we're going to interpret even the phase diagram or the vapor pressure diagram for an ideal solution. Maybe let me hear from Mwesigwa Esther. Yes, Esther?
Yes.
Mm, yes, please.
Sir.
Good afternoon.
Master, I've just arrived in this lesson. So my question is there is phase
Yes.
diagrams which they used to ask the other phase diagrams of carbon dioxide, water, and sulfur. So our teacher told us that those phase diagrams were scrapped off. So I don't know whether it's correct. That's my question. Are they still
Oh,
examined?
no, those ones for sulfur, for carbon dioxide, they are not part of the syllabus.
So they are
Yeah?
not examined.
Yes, what is not part of the syllabus is not examinable. And there's no need of teaching it. You get? But when you talk about ideal solution, maybe after, but I'm going to share the syllabus to you in the chat later after the lesson. You'll be able to see, you follow. When you go to these subtopics under Equilibria 2, you see the subtopics there, and you can even be able to see the content. So those ones are not part of the syllabus. That's why we don't take time to teach them. That's why when you see me today, I've just started from Laut's law and I had to go to ideal what? Solutions. You get?
Yes, Master.
Esther,
Thank you so much.
okay, you're welcome. Shinaguz, unmute. Shina, yes.
Excuse me, teacher. What do you best want to tell that these are examples of ideal solutions? Can I say also benzene and hexane is an ideal solution, or?
No. These examples we base on their characteristics. Now, right now for you may not be knowing their characteristics, but through research and looking at what has been discovered already, that's when we can be able to get the examples. You get? So it's not any example that we give will be falling under ideal solution. There are those which are not. Others, they deviate from ideal solution. And there's an NB I want us to note down here. Maybe let me just write it here. And I say, let me just note it here. Where are you? Here. Which, just a minute, and I know it was. If I can use another color like blue, there's this NB. This NB says that ideal solutions do not exist. Do not exist. However, the ones mentioned above, the one we have already mentioned, approximate. They approximate to the ideal behavior. I wanted to put this one clear, that in real life, you may not find the one which act very well, obeys the Lao's law very, 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 very well. But there are those which are some approximately related, giving us this ideal what? Behavior. So those are the ones that we have been able to mention there. Now, I would like us to consider the binary liquid. Someone is brought very many questions here. It's okay. I will answer them and then you can move on. Sammy Plokes.
Good afternoon, sir.
Good afternoon.
According to the note, that the ideal solutions do not exist, but they approximate. So, like in the characteristics, can I give that intermolecular forces are approximately equal?
No. No. Don't say approximately. Now, the characteristics are going to remain. But these ones we are getting, they are almost like, if you recall, when we approximate that one which has very, very small errors. So when you look at these ones, they have very small error if you are to look at, but the other ones, they deviate completely. Others are not giving something which is related to the one for an ideal solution. So if you find out that in a good ideal solution, there's no heat change during mixing. But here you may find that very, very, very small change has taken place, but very, very what? Small. So just this note is telling us that it is not purely ideal, but approximate to a very big extent. They show us these characteristics. So we can't adjust the characteristics of ideal solution to fit the examples. So our characteristics remain the same. Are we there? Okay, now let's consider this. Let's consider this example. So when you consider a binary liquid mixture, when you talk about binary, the other time it was confusing people. Binary, the mixture having two, substances. Do you call binary base? Base what? Okay, people have disappeared. Can I move with one person? Yes, Esther. Esther has run. Esther, put up the hand again. I want to move with someone. Okay, Nasa. Yes, Nasa?
Yes, I'm here.
Okay, let's move together, yeah?
Yes.
Nasa, we are going to move. So right here, I want us to understand more about ideal solution and those characteristics we have been looking at. And we want to see if you consider a binary liquid mixture, which is made up of a component A and B. Are we there? Now, we're saying that the total vapor pressure, we are going to be considering what we have been talking about, the characteristics. We are saying that the total vapor pressure exerted above the liquid mixture is given by the expression. Yes, please. Which expression do you think is that?
I think it is A plus B.
Okay. The total vapor pressure, meaning if you say that the total vapor pressure, P total, will equal to the one for A plus the one for B, isn't it? That's what we have
Yes.
already noted down. Okay, very good. But, do you recall what Laut's law tells us from Laut's law?
Yes.
Laut's law told us that the partial vapor pressure of A is equal to what? I want us to move with also a lady. Lydia, you unmute. We move two people. Lydia? Lydia, unmute faster. Lydia? Okay, good. Lydia, are you also there?
Yes, teacher.
We are going to move together. Three people now. What did the Lord's law say? The partial vapor pressure of A is equal to
Partial pressure of pure air
partial pressure of pure air times what?
is small fraction.
Its small
It's small.
fraction. Isn't it?
Yes.
Meaning, if we want also for B, even if the one for B to be partial vapor pressure of B will equal to what?
It's small fraction. Partial pressure
Partial pressure
of B.
of pure B times the mole fraction of B.
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 Are we there?
Yes.
Are
Yes.
you seeing that? Meaning we can have, this implies that P total can also be written as, because PA we have it now as this. So we can write it as, maybe, can I put more fraction behind P like that? Yeah? Plus
Yes.
this one. I have the mole fraction first times the partial vapor pressure of B. Are we all agreeing that that is true?
Yes.
Yes.
But you recall, this is mole fraction of A, and this is mole fraction of B.
B.
What is the total mole fraction? When you get mole fraction of A plus mole fraction of B, what do you get?
1.
You get a 1.
1.
Are you seeing
1.
that? Meaning,
Yes.
if I want to get the mole fraction of A, I can make it the subject and then becomes 1 minus mole fraction of B.
B.
I want us to look at that. Are we there?
Yes.
Yes.
Or we can say mole fraction of B is equal to 1 minus mole fraction of A,
A.
which is still the same. I believe I've not changed anything. We are just following from what we started with here. Okay, so what does it mean? Meaning that our P total can also now be written as, you call our P total at a given point, we had it like this. So we are going to substitute. Maybe we can first substitute the value for mole fraction of A. Yeah? Or we can first put the value for mole fraction of B. We can start with any. Let's start substituting the one for B, meaning it will be mole fraction of A times pure A. I've put for this one, then plus. Now we substitute the value of mole fraction of B is given as that. So it is 1 minus mole fraction of what? A times the pure what? B.
B.
Are we moving together?
Yes.
Yes.
Yeah, so if we open brackets there, what do we remain with? Meaning our P total will equal to XA P naught A plus P naught B minus, are you seeing this? This one.
Yes.
Yes.
We multiply with the 1. Then when we open brackets, becomes minus mole fraction of A times P naught what? B.
P not B.
Yes.
So if you collect these ones together, I will collect them towards one another there. It will be mole fraction of A, P naught A minus mole fraction A, P naught what? B plus P naught B. Is that clear?
Yes.
I've just collected like this one I brought it towards the other end. Meaning at the end of it all, we can make mole fraction of A a subject. It becomes P total equal to P naught A minus P naught B in brackets, the mole fraction of A plus P naught B. Are we together?
Yes, sir.
Yes.
Hello? Are we together?
Yes, sir.
Yes.
Now, when you look at that, are you seeing that we are getting almost something related to an equation, which is like y, if this is our y equal to mx plus c. Now, this one becomes our constant. What does it bring to us? It is what I'm trying to bring to our attention is that when you're drawing the vapor phase diagram for an ideal solution is a straight line. Okay, it is in the form of a what? A line. Have you seen that? Is
Yes,
in the form
teacher.
Yes.
of a line. And we can also do the same for the other one. Instead of substituting mole fraction of A, we can also substitute mole fraction of B. And we have for the other one. I don't know whether we can try it out very fast. Let me change the color so that we don't get disturbed. Here. Now, look at this. If I change, instead of substituting here, value of the mole fraction of B, if instead of substituting for this, I can substitute for this one. Meaning our P total will equal to the mole fraction of A, we say it is 1 minus mole fraction of B, then we multiply by B. No. This is it. A. Are you seeing it that, Lydia?
Yes, teacher.
Then plus mole fraction of B times the pure B. Then what is next is just mathematics. So meaning it will be P total equal to open brackets. Now, be speaking. Open brackets there, it will be 1 times this, it will be P naught A minus this times that, it will be mole fraction of B times P naught A
A.
plus mole fraction of B times P naught B. Then
B.
we can make the other ones. This one will be, if you collect like terms together, meaning in brackets, we can have P naught B minus. Some of you are going to get confused here, but let me hope you're not. Plus P naught A. I want to be sure that everyone is able to internalize that.
Teacher, excuse me.
Yes.
Will you pardon on that on starting P total?
Where? Here?
P total in
Oh,
red, in pink.
in red. Okay.
Yes.
Now I'm going to just change something here to this. Okay. I believe this pointer you're seeing it.
Yes.
Now, when we are looking at actually where is it starting from? From here. Look at this. We are saying that P total is equal to mole fraction of A times pure A plus mole fraction of B plus times pure B. I believe this one, you know where it came from.
Yes.
Now, I want us to substitute in this equation the value of mole fraction of A, this one. So, and you say that mole fraction A is equal to 1 minus the one for B.
B.
Are we there?
Yes.
So when you come here, that's why we're having the P total equal to the mole fraction of A, which is 1 minus mole fraction of B, times the vapor pressure of pure A, plus mole fraction of B times vapor pressure of pure B. This one has remained the way it was. Are we there?
Yes.
Now here we open
Yes.
brackets. So when you open brackets, meaning it will be 1 times P naught A, which will be P A naught A minus mole fraction of B times P naught A, which is this one. Then we add mole fraction of B times P naught B. Now, what I've done here is making, you see this one and this, they have something in common. What is in common on them? These two. Are you seeing that mole fraction of B is common? So that's why I've put it where? Out. I have factorized it out here. So when I factorized it out, you can see, because I don't want to have negative, I said, let me start with the one for pure B. So I said pure B minus pure A, in brackets, I put our mole fraction of B. Then plus
B.
this one. Are you seeing that?
Yes.
So at the
Yes.
end of it all, are you seeing that the one for pure, the one for this one, vapor pressure of A, pure A, is now our constant, now at this point. And then our gradient M and our X is the mole fraction. So when we are drawing the diagrams for ideal solution, you'll see that we are applying actually this. We will see that there are straight lines, and where the straight lines coming from, it's from what we have already seen here. Now, maybe what will be next? What will be next here is just helping us understand what is this, what is each of these standing for. But I believe we already know what each is standing for. Here we can say where, look at this. If you look at this first equation, let us call this equation 1, and this one is our equation what? 2. Are we there?
2.
So we're saying,
Yes.
I'm going to list them, and you'll be telling me what they mean. The first one is P total. The second one is P naught A. Another one is P naught B. Another one is this one. Another one, I believe for this one is done. Then we come to this one. When you come to this, look at it very well. The other ones, we have already talked about them. What is remaining is X. Okay, P total stands for what?
Total pressure.
It is total vapor pressure above the liquid mixture. Above
The liquid
the
mixture.
liquid mixture. Okay, good. Then P naught A is what?
Vapor pressure of
component A.
It is vapor pressure, not partial. It is vapor pressure of component
A.
Then this one is vapor pressure of component B. I think we don't need to write it. XA is what?
Mole fraction of component A.
Mole fraction of component A. And then this one, mole fraction of component B. Are we there? Now, finally, yes, please.
Teacher, is it not necessary to write the vapor pressure of pure A?
This is vapor pressure of pure component A, we need to put it here, of pure component A. Isn't it?
Yes.
Yes.
Because this is different from this. Now, this one is partial. This is partial vapor pressure of component
A.
A. Not pure. Even this one is partial vapor pressure of component B. Are we there? But what have we seen? We have seen that the total pressure of a substance, when we do the calculation, the whole thing ends up as if it is a straight line, giving us something related to a straight line, having the y-axis, the x-axis, having the gradient, having the constant, a line. That's why when you go to the next slide, we shall be able to see how a vapor pressure composition diagram looks like and even how we can interpret it. Thank you very much for those who have been following with us, the two people, that is Lydia and NASA. Thank you very much. We can have now Kayondo. Kayondo, your hand is up.
Yes, Master. For me, but of course, I heard you say that you shall help us get to know how to interpret those diagrams.
Oh,
So now
that's
my
where we are
hand
going.
should be down.
No,
Yes,
your
thank
hand,
you.
let it be up, and then you interpret for us. Here we are. The vapor pressure composition diagram for an ideal mixture of component A and B. Are we there? Kayondo?
Yes,
So Kayondo,
I'm there.
so on the previous slide here, we have been able to calculate, understand when we have a mixture of two components and they obey Lord's law, we see that it ends up as a straight line. Yeah, okay.
Yes,
Equation of a
yes,
line. Are we there? Now, when you come here, we want to
yes,
look at the diagram, which is there.
yes,
Have you been able to see the diagram? So in this diagram, we
yes, Master,
see
I'm seeing.
this is PA. We have already seen that is the partial vapor pressure of component A. This is the partial vapor pressure of component B. And we are seeing it is
B.
a straight line coming from 0. Yeah. Now look at
Yes,
down here. Down here,
yes,
the down part is having the mole fraction. The mole
molar,
fraction.
mole fraction,
Yeah. And when you see here, yeah, mole fraction of A, this side, it starts when it is 0, it keeps on increasing until when it reaches this side where it
0,
is 1. So maximum is 1.
1.
Even when you're moving this side, the
Yes,
maximum is 1 for B.
yes,
So in simple terms, when we are looking at the diagram for an ideal mixture, composition diagram for an ideal mixture, this is how we are able to draw it. And I don't know whether all of these ones we have already calculated them, where we are saying
yes,
that PB is equal to the mole fraction of B times this, and but now you can see initially when we are beginning at initial point, PB is equal to P
P0.
P naught,
Eh,
isn't it?
yes,
Yeah. So even the same case for PA initially, when we're beginning, PA is equal to P naught, but it keeps on changing.
P0.
That's why you see it keeps on changing with changing the mole fraction. Also, this one keeps on what? Changing. That's why you see a very good
Changing
straight line, a
line.
uniform line. And here they're
Yes,
telling us that the mole fraction, when you get A, and then for B, you get a
you
what?
get 1.
1.
1.
One thing we need to know is that as we move, maybe if I can just show with a pointer here, like when you're moving on this line, as you move from this end going to the other end, as you're moving and the mole fraction is increasing from this side, as it increases, the other one is decreasing. Like at any given point, the mole fraction of A plus the one for B, it is equal to 1. What does it mean? It
Yes,
means that if A is at 0.2, meaning B is at 0.8.
0.8.
I believe that one is very clear.
Yes.
Yeah. Unless someone has a question, but I want to just interpret a few things here, though we have already interpreted them by writing on the side. But let me see other things that we can write or note on this point. Okay. Just noting a few things here. What we can note here, we're saying that
Yes.
component A and component B. One thing we know, they are completely miscible. They are completely miscible.
Miscible with each other.
Yes, miscible, meaning they can mix with one another uniformly. Yeah. Then we're saying that the mole fraction of A, the mole fraction of A, we have already seen that if you have mole fraction of A and that one for B, the maximum will equal to 1. Yeah. Hello.
Yes.
So when you look at
Yes, Master, I'm there.
this, the mole fraction of A at the end this side, it is what? 1. Meaning for B is 0 at this
1.
point. Are we there? If X is A at
Yes.
this point, then B is 0 at
Yes.
that point. So as it keeps on decreasing, the other one also is increasing.
Point.
So we're saying that as the proportion of B
Increasing.
increases, as the proportion of B increases, the proportion of B as it increases, B increases from this side, yeah? As the proportion of B is increasing, yeah?
Yes.
The mole fraction of A
Yes.
in a vapor also
Yes.
decreases. So as B is increasing going this side, for the A is decreasing. And this also decreases the saturated vapor pressure.
Decreasing.
Yeah, decreases the saturated vapor pressure of A along the line PA, along the line P. This is our line PA, along the line PA, until it
Yes.
reaches at X equal to 0. It keeps on increasing and decreasing until it reaches at X equal to 0.
0.
So as the fraction of B
0.
increases, the one for A is decreasing until when it reaches at this point at A equal to 0. And the same thing happens as A is increasing. B is also decreasing along this line until when B,
Decreasing.
the mole fraction of B is equal to 0. I don't know whether we have any inquiry, but for me at that point I'm done. But I want to give you an NB, and we are saying that NB, the saturated vapor pressure, of pure A is greater, than that of pure B, because A is more volatile. A is more volatile than B. Thus, at a constant temperature, A exerts a greater vapor pressure than B. This point I have noted down here. We're just saying that the saturated vapor pressure of pure A is greater than that of pure B. We see that on our diagram. When we look at B and A is a little bit higher than what? B. Are we seeing that? And they're telling us that the reason why A is higher than that one of B is because A is more volatile than B,
Volatile than B.
volatile, more volatile than B, and thus
B.
at a constant temperature, it exerts a greater vapor pressure than B, since it is more volatile.
Volatile.
Okay, that is my explanation for that, unless someone has a question. Thank you. Asime Dola is saying thank you. Wafula John, you have a hand up.
Yes, teacher. Good afternoon.
Good afternoon.
Now my question was,
Mm,
one has been answered about which one is more volatile, and then the second, most
mm,
of the programs I have seen in
mm.
some texts usually have labels assigned to the diagram, I think for better understanding. So I was kindly requesting if you could help us label the diagram, probably where the liquid is and then also the vapor phase.
Oh, labeling the
Yes,
diagram so that we can be able to know where the vapor phase is and where the liquid
the
phase
liquid,
is.
yes, for easy
Okay, thank
understand.
you. Thank you very much. So under this line, this one, that's why we have the vapor phase. That's why we have the vapor phase. Then if you come above the line this side, that's why we have the liquid phase. Thank you very much. Yeah, I think in the preceding diagrams, we shall be able to show all that. Then the reason why I have not named the P naught A, P naught B is because we have already labeled them in the previous slide, showing what this one is, what all these are. We have already discussed them. And the reason why these lines are straight, we have already calculated and gotten that, showing us an equation of a line. But the vapor phase is under, and then you have the liquid phase on top. Asime Deborah, you have a question?
Yes, teacher.
Mm,
According to the diagram I have here, it shows that according to the interpretation,
mm,
when I'm basing on the interpretation of this diagram you've given us,
mm.
for me, my diagram shows that B is more volatile. Is there instances that we shall have B being more volatile than A?
Do you have some instances when B is more volatile? It depends on how you have drawn your diagram.
Yes,
The
because here
one,
my
there's the one which has vapor pressure which is small, and the one which is having a vapor pressure which is very high. So the one which is having a high vapor pressure and the one which is having a low vapor pressure, which one is more volatile than the other? That is the question I think we need to look at. Because when we give you a question and you're to draw the diagram showing that, you'll base on the values to know which one is above and which one is low. So,
teacher, my
Deborah,
question.
mm,
Yes, please, teacher. My
yes,
my question was,
yes.
is it just necessary? Okay, it is not necessary for A to be more volatile than B. It's just according to the question.
Oh, Auntie, you call A is not, just A is representing any what?
Any
Any
pure thing.
substance, yeah?
Mm, mm.
Because it could be maybe the one between benzene and methyl benzene. So A could be maybe benzene, B it could be methyl benzene. But which one are you going to put on A, which one are you going to put on B? It will depend on the vapor pressure they have given you. For example, if meaning like here, maybe the one for A was maybe like 540 mil of mercury. Then for B, now B, because it is low, maybe B it was around 500. Are you seeing? And
Yes,
it's not
teacher.
a must. It's not a must that the diagram should be facing on the other end. You can have your diagram which is like this. Let me use maybe red here. Let me use maybe red here. Do you know that you can have your diagram which is like this, and maybe your 500, the one for A is here, and this then the one for B is down. No. This one is for B, and then the A is on the other end. This one can also happen. You can draw it in that manner. Sorry. Okay, it has just jumped off. Just give me a minute. No. Minute. Where is it? Here. Okay, we are back. It is there. Then this one coming on the other end. So it's not a must that A has to be on this side and B on the other side. It depends on which question they have asked you. Even the one which is higher can be on this side. Is this the right? On the right hand side, and then the one which is low is on the left hand. So depending on what they have given you, meaning our total will be on top there, like that. Deborah, are you still there? Deborah has gone. Okay, Tricia. Let me hope I've answered Deborah. If not, please you raise your hand again. Tricia.
Good afternoon, sir.
Good afternoon.
Sir, for me, what I'm inquiring is about those phases. How do you know that you're having the liquid phase above and the vapor phase below? As in, what do we consider?
Oh, no, Auntie, when you recall, we are not going to look at what you're going to consider or we're making it static. There's no one day when the liquid phase will be below the vapor phase. So mostly when we mix the two, the liquid phase will be on above, and then the vapor phase is always below. You recall we are mixing the two, component A, and then the component B. And these are vapor pressure composition diagram. Vapor pressure composition diagrams.
I've got it. Thank you, sir.
Yes. Welcome. Allow me move on. Seth, you'll be the last one.
Okay.
Seth.
Thank you, sir. So, sir, when you were deriving the expressions, you said that on the y-axis we were supposed to put there the total pressure, but then now we are putting the pressure for the pure A and pure B. Then also,
First wait. What did you say?
You say when you were deriving the equations, you said that on the y-axis we are supposed to put total pressure. But here in this case, we are putting the pressure of pure A and the pressure of pure B.
Oh, no, you recall. Look at this. Our equation was like this. It is y equal to mx plus c. And here on this end, it was P total equal to, I don't know what was in brackets, but maybe PA naught minus PB naught lambda. Is this B or A?
A.
Okay, A plus, what was the constant here?
I don't remember. The constant, I don't remember.
Okay. A good thing we have them here. Okay. Are they these ones here? They are here. Where is it? The one we are considering PB minus A. Let me see whether it is the one we have considered. PB minus A. Okay. So we can consider one of the two. Which one can we consider? Let's consider PA naught minus PB naught. If we have PA naught minus PB naught. Is it that one? No, it is PB minus PA naught, then times the mole fraction of B, then plus PA naught. Isn't it?
Yes,
So
teacher.
I want to know, what was your question?
So in this expression,
Mm,
we said that the y-axis has to be with P total, but then now our y-axis has the pressure.
now you
What?
see,
Mm.
when let's consider this one, yeah.
Okay.
Are we
Okay.
there?
Yes,
So when
teacher.
you consider this, meaning at this point, mole fraction of B is equal to 0. When you come this side, at this end, mole fraction of B is equal to 1. Tuko pamoja?
Yes, teacher.
Now, substitute. If the mole fraction of B is equal to 0, the whole of this will be 0. Meaning, at this point, we have PA naught. Our constant is PA naught. Are you seeing that is the one there?
Yes, teacher.
Look at this. Are you seeing that?
Mm.
Meaning P total is equal to PA naught. At this point, even P total is here. That's why you're seeing that P total is starting at this point.
Yes,
But
teacher.
as the mole fraction increases, there is what is happening. The other one is also decreasing. So at one point, at all points, mole fraction of A plus mole fraction of B will always equal to 1. If this one increases to 0.2, the other one will be 0.8. It keeps on moving on in that manner. So our equation is very true.
Okay. Then also here in the first expression, in these expressions that are on the right, you said
Here.
that, yes, you said that the pure pressure of B is equal to partial vapor pressure of B. But then isn't it like originally that there is no partial vapor pressure because they have not yet mixed up?
And initially, the partial vapor pressure, why are we saying it is equal to the other one? Partial vapor pressure of this is equal to vapor pressure
The
of B.
B.
And there's someone who was answering that question. Who was that? Anyone who has had that question and you want to answer it? There's someone who had answered it. Only that some of them are not raising up the hands. Anyone there? Okay. Okay, so where is this one coming from? Hello? Faith, are you still there? Yes. Faith has muted. Faith, can you unmute again?
Teacher,
Please
I'm there. Okay.
don't mute before we are done.
Okay.
Okay, so we are still here. Now, you recall at this point,
Yes, teacher.
are we there? The
Yes.
mole fraction of B is equal to, read for me, what is the mole fraction of B at this point?
Where?
Let me,
Where?
here, at this end. The mole fraction of B is
It is equal to 1.
equal to 1. Are we there?
Mm.
Now, if it is equal to 1, let's
Mm.
substitute, and you see where it is coming from here. So if it is equal to 1, we know that partial vapor pressure, that one also, okay. We know that partial vapor pressure of B is equal to the mole fraction of B times vapor pressure of pure B. But mole fraction is equal to what?
Is
Is
equal to
equal to,
1. 1.
therefore, P naught B is equal to vapor pressure this. Have you seen where it is coming from?
Yes, teacher.
So this one is true at this point. But as we move on, it no longer becomes true. As we move on, then this one works. I don't know whether you have got it right now there.
I've gotten. Thank you so much, sir.
Okay, welcome. And since we have already interpreted this, I will not take much time on that. We have already explained it. I would left this space for us to discuss, but we have been able to discuss. I have a practice question, 5 minutes practice. Get your answers and put in the chat. 5 minutes. For me, time management is very important, meaning at 35 minutes past 3, we should be done with that item. Maybe I have one person to read for us the item. Take a screenshot, try and do it. After 5 minutes, we should be done. There's someone called Azeotrope. Azeotrope, when you reach on Azeotropes, you'll be able to answer. Azeotrope, unmute. Azeotrope, unmute. Azeotrope. Okay. Yes. Azeotrope, what
Okay.
is your name?
Esther.
Esther, when you reach on Azeotrope on Tuesday, you're the one who is going to take us through the whole topic about boiling point composition diagrams, deviations, and you explain for us Azeotropes, yeah?
Yes.
So make research next week on Tuesday, you'll be able to take us through. So read for us that item, and then each and everyone should be practicing, doing it in your book, apply what you have learned, and then I see whether you are getting it or whether we are not yet there. Read for us that.
Okay. Practice item. Calculate the vapor pressure above the solution containing 50 grams of heptane and 38 grams of octane at 20 degrees Celsius. The vapor pressure of pure heptane at 20 degrees Celsius is 473.2 pascals, and that of octane at the same temperature is 139.8 pascals. The carbon is 12, hydrogen is 1.
The turn is yours to put down, and I want the answers in the chat. Let's begin. So there is a link that I have put in the chat. Let's continue to utilize it very well. Click there, you subscribe there, and then you can always follow for other discussion for each and every topic, because we have put one for inorganic, we have put for organic chemistry, and the inorganic and physical chemistry. So have time and subscribe, but also share with your friends who are not part of our lessons so that they can always benefit from whatever we discuss. So someone, Alpha, has already gotten the answer. Alpha, we shall be able to see whether that answer is the right one. Has gotten the answer. Please put even the units. They have asked us to put, let me see, calculate the vapor pressure above the solution containing, meaning they just want us to get the total vapor pressure. And we already know the formula for determining total vapor pressure. I think that should be something very simple for us to do very fast. Containing 50 grams of heptane. They have given us the mass for heptane, at 80 grams of octane. So you already have mass for octane. This is at 20 degrees Celsius. Then they're telling us the vapor pressure of pure heptane is this. At 20 degrees Celsius is that. And that of octane at the same temperature is that. Then we should be good to go. Let me check in the chat whether people are getting the answers. Someone is saying, Samsung is saying 340 pascals. Let me see whether your answer is right. See whether your answer is right. Aha, Samsung, your answer has a problem. Actually, your answer, let me give you the answer. Check whether you have this answer. Okay, let me not give it to you. Try it by yourself. Someone is saying 339.840. These are two people who have gotten this. 339.84 pascals. Okay. It is somehow related to the answer, but not the right answer. So even that one has an issue. Let's continue. But at NASA Elix, thank you. Me too. Pecos, you're saying me too. What is me too? Put your answer there. Someone else, Andrew, is saying 332.009. Please reshare the link. The link for it is there. You can get the link. So 332.009 is not right. Please make sure you subscribe there so that you don't miss out anything that we share at any particular time. And then when you go there, check in the playlist. Look for physical chemistry, look for assessment, look for guidelines. They are all there. You'll be able to get all that work. Pecos is getting now 339.84. Okay, the answer is not there. I want to see someone who is getting around 348 something. Pecos, you're still in 339. Trisha has 329. So I think our time is done. Lydia is getting 356. No, Lydia, it is missing. Doctor, 317. It is missing. You're missing out something. Doctor, you're missing out something. 317 is not the right answer. Azeotrope has gotten a 3. Azeotrope is getting what? 365. No, you're missing out. Andrew, he has gotten now 334. Oh, no. We have Chemaria. Chemari has gotten 263. No, Narienda 33. Alpha 348. Alpha is saying, how can 348 be the answer? I'm not saying it is the right answer, but there are some decimals there. Okay, thank you. But at least I see that we are all moving together, and I want us to... can I have one person who has already calculated, and then we move together? Hey. Someone who has already calculated and we move together. Lydia, unmute. You tell me whether you have a calculator. Do you have a calculator?
Teacher, I have.
Okay, now that you have a calculator, let's move together and we confirm those answers that we have. So what do you think? Where do you think we need to start from?
The molar masses of each compound.
Okay, let's also move with Kayondo.
Excuse me, teacher.
Kayondo?
I'm getting 345.041. I'm getting 345.04102.
345.01. This one, Kayondo.
345.01. Yes.
Okay.
But that one is 4.
Auntie,
102.
01. Okay, now you remain on the microphone. We move with Lydia and you. We see whether your answer is correct or it has an issue. Lydia, for you, what did you get?
356.8434.
Let's confirm who is right. The good thing you're all here. So what do we start with? Molar masses. Okay, good. Let's get the molar masses. I'm going to be writing very fast. I want your calculators to be very active. Your
Okay.
calculators should be very active. Oh.
Okay.
Okay. Sorry, I'm just looking for my
We start
whatever here. Okay. I was
we
still
start
looking
looking
for
for
my.
the masses.
Okay, so let's start with molar mass of what? Heptane.
Heptane.
Heptane, that is
Heptane.
C7 He16.
H6.
So meaning that will be 7 times 12 plus 16 times 1. What is the answer?
100.
The answer is 100
It's
grams.
100.
Hey, now you see how you got it wrong. Okay, for you, do you have that? Lydia?
Yes, I have.
Okay,
The
now let's
Malay
go to molar mass.
I had 86.
Now that's why you get the answer wrong. Now let's go to octane. 8, 6, and then H18.
Okay.
Let's try it out. This is 8 times 12. 18 times 1. What is the answer?
I used 10.
How
Is,
many did you?
114.
114.
Yes, 116.
Did you get that?
No.
You see where the marks are, where you're not getting wrong, now the score ones. Okay.
So we have failed
Okay.
on the naming because we thought 10.
Yeah,
Okay.
heptane and the octane. So hept is 7 and then oct is 8. Now from there we look for what?
Teacher, excuse me.
Mm.
Teacher thought octane is 10. That's what I messed up.
No, octane is 8 from the word octagon.
Okay.
Let's always recall from those shapes.
Okay.
Octagon. Yeah. From molar mass we look for what?
So master octagon, I thought it's 10. Okay.
Octagon.
We
And
divide.
octagon, those are
you get for heptane, you will get 50.
And we are looking for the number of moles now.
8.
We first get the number of moles of octane.
Yes, we are getting.
Okay, for heptane, and then we also get the number of moles for heptane. So here,
so we
number of moles
the
is equal
other
to
one.
mass. Mass is
We get
38.
50 divided by 100.
Why are you getting 50? Okay.
We are first getting.
Okay, yes, 50 divided by
100.
100.
What is the answer? That is what?
0.5.
0.5
Are you seeing that?
moles.
Okay, good. Now on octane, it will be 38 grams over 114 grams. What is the answer?
0.3 recurring.
0.333 recurring.
Okay, 0.3 moles. Since we have taken one decimal. So after getting moles, what next?
Total moles.
So what will be the total moles?
We now get the total.
0.5 plus 0.3. And we are first getting total moles, which is 0.8 moles. Then from there we can first get
0.8.
From there we look for
mole fraction of each.
Mole fraction. But before we look for mole fraction, can't we first get our formula? P total is equal to We say that, okay, XAPA. What is A? Octagon. Octagon, P not octagon, plus X heptagon.
Yes.
Yeah? Then P not H.
Yes.
But, do we have all of these?
Yes.
Do you have all of these?
Yes, master. Yes.
Let's see. They gave us vapor pressure of pure heptane. Oh, so we have these ones. Yeah?
Yes.
Meaning,
Yes.
we can just substitute and
Yeah.
we get done. So we just need a more fraction of this and more fraction for that. And then we get it done. Okay. Can we get more fraction? XO. XO will be what?
0.3 divided
0.3 divided by
0.8.
0.8. Then XH will equal to
0.5.
0.5 over 0.8. Isn't it? Meaning now we can just substitute.
Yes.
P total,
Yes, master.
P total will be X naught. We have gotten 0.3
Yes.
over 0.8
Equal to
times this. P naught for octane, what is that? 473.2.
Octane. Teacher, no.
Octane, isn't it this one?
Not
we are
really.
starting with master the other one. No. No, octane is one.
Okay.
Octane is 139.8.
Okay, nice. Now I can see we are there. So here it is 139.8. Okay. Then for XH is 0.5 over 0.8 times 473.2. Okay, get me the answer here. Use your calculator. Now your answer should be at least to 4 decimal places.
$52.4.
52.4. 4 decimal places.
25.
52.25. 52.425. Master, on the first one, it is 52.425. Nafanya 345.04102. Bahise kufuna pito ntudwayo just ya tulisambo question giki twatandikira started from slow nashemesa ideal solution. Kakanje kalya yiga kiri abaana bato de kata abona n'olugomba shoma kami Mr. Zen what? Yes.
Kayondo?
Yes.
Wafunachi.
Nafnachi. Yes. Let me come. I will get back to you. Having a lesson.
After the answer, the correct one. Kayondo? Hello? Nganda kumambona n'abanyankole nsobora hata hana funeki kumangoni bachura. I don't know. I don't know what's happening, please. You just screenshot the items. You screenshot the paper. You'll be screenshotting. You never know that it is coming back. People be screenshotting.
Hello. I can see many people have gone back. Regan, where are you? Regan, I've been telling him to unmute, but I've been here for some time, but no one is unmuting.
Teacher, I'm there.
So I don't know what had happened, but I think now we can move on.
Yes.
I can see the number has dropped significantly. So I want us to use a few minutes and we wind up with this session. And I just want to bring back where we had reached. So I was asking us to give us the result here. What did we get here? The one I was moving with, was it Lydia?
Yes, teacher.
What did you get on this?
295.
295.
0.75.
0.75. Let me first work on these people who have started dating our screen. 295.75. So the final answer becomes
348.
348.175 pascals. I believe you see the response. The answer was telling you that is the one which I wanted us to get. There's someone who was saying, don't you first calculate the individual partial pressures? You can first calculate them and then you use this formula, because we also have this formula that P total is equal to PA plus PB. So if you get this and this, you just add it and you get the answer. Because PA is the same as having the whole of this, PB is having the whole of this. So in simple terms, it is the same formula, but just summarizing it in that manner, since we had already discussed. Let me hope that is very clear. I want us to move on to our next slide, where we are looking at the real solutions. Of course, because of that which happened, our time, I see it is already 4. We need to agree how many minutes we need to give ourselves, and then we can see. In a chart, how many minutes should we give ourselves? How many minutes can we give ourselves? Someone is saying 30 minutes. Okay, let's use 30 minutes after 30 minutes, we should end there. And I believe in 30 minutes, we should be also done. So allow me to move a little bit faster as we continue to understand these concepts. So when you talk about real solutions, we have finished looking at the ideal solutions. Ideal solutions, and that is done. And now here, we want to understand what a real solution is, or what you're calling a non-ideal solution. What is a non-ideal solution? Let me just use the chart. What is a non-ideal solution, or what you're calling an ideal solution? Let me see your answer here in the chat. Are we not going to look at boiling point composition diagram? Like I said, that one, we can look at it in the next session because of time. So let us first look at non-ideal solutions. And when you're looking at non-ideal solutions, that's where we see the deviations from ideal solution, the positive deviation and the negative deviation. So someone is saying the reverse of ideal solution. What is the reverse? John Paul, please. Solution that doesn't obey Laut's law. Good. Lubega Regan is giving us that solution that doesn't obey Laut's law is the one you're calling the non-ideal solution. So we can move on with that. So here we have it, and they're saying that a non-ideal solution is the one which doesn't obey Laut's law rigidly. The one which doesn't obey Laut's law rigidly. And they're saying that there are two types of non-ideal solutions. In the chart, which types are those? Let's put them there. How many types of non-ideal solutions do we know? Lubega is saying, okay, Lubega has noted. Who is giving us the answer? There are two types of non-ideal solutions, namely, number one. Can I have number one in the chat? Types of non-ideal solution. If I can see one person with a hand up also, no issues. If you can raise up the hand and tell us. Okay, Joshua is saying a non-ideal solution is the one in which the cohesive and adhesive forces are not equal and does not obey Laut's law. Good, that's the definition. I think one is azeotropic solution. Okay, azeotropic solution. Quantum is saying a positive deviation and a negative deviation. Okay, thank you for your submissions. So when you talk about two types of non-ideal solution, like Quantum is saying, there are two, and one is those that deviate positively from ideal behavior, and the other ones which deviate negatively from ideal behavior. So there are two types. One which deviate positively and the one which deviate negatively. And I would like us to start with the one which deviate positively, the positive deviation from ideal solution. And what are we saying? That in positive deviation, it occurs when a solution shows a higher vapor pressure than expected from Laut's law. Lydia, you're having your hand up. Yes, please.
Teacher, I wanted to give the types of non-ideal.
Oh, the types of non-ideal. So the one is what?
Positive and negative deviation.
The positive and negative deviation. And now here we are looking at the positive deviation, and are saying that for one to be called positive deviation, it occurs when the solution shows a higher vapor pressure than expected. What is expected? The expected is for it to be straight, like the way we have seen already in ideal solution. But the one which shows the one which a little bit higher, then we say that one is a positive deviation, or it is positively deviating from ideal behavior. Mwesigwa Esther, you have a question? Yes, Mwesugwa? Okay, we can move on. So we are saying that this happens because the intermolecular forces between the unlike molecules, so the intermolecular forces between component A and component B are weaker than those for the individual component or the pure components AA and BB, which is different from the other one for ideal. For ideal, both AB, AA, BB, all those ones were almost the same. They are uniform. But this time around, we see the intermolecular force of attraction between the unlike, the mixture, they are weaker than those ones for the like molecules. So how can we explain this? So here is a simple explanation. And they're saying that when two liquids are mixed, the molecules attract each other less strongly. So these molecules escape more easily into the vapor phase. And then the vapor pressure increases above the ideal value. So that is why we see that the intermolecular force of attraction is higher, or it shows a higher vapor pressure than the expected. Why? Because when the molecules attract one another, they attract one another more less strongly, and at the end of it all, these molecules escape more easily because the attraction is not very strong. So the molecules can easily escape. And when they easily escape to the vapor phase, even the vapor pressure increases above the ideal value. So that is what happens during the positive deviation. Then, therefore, the solution boils more easily, and then the boiling point decreases. That is what happened during the positive deviation. Now, what are some of the characteristics of positive deviation? If you can just have only two responses, who can give us some characteristics of positive deviation? From the definition, we can get some, but also from what you already know. What are some of the characteristics of solutions that positively deviate from ideal behavior? Anyone? Yes, Lydia? Okay, Asimwe Debula first. Hey, Asimwe, unmute again.
Okay, these are the properties of these mixtures that deviate positively from Raoult's law have that heat energy is absorbed.
Okay. Heat energy is absorbed. Continue. Yes. Asimwe. Aite also unmute. We move together.
Yes.
Aite.
Total volume. So it means that when these
Teacher, my answer is the total vapor pressure is the total vapor pressure above the liquid is greater than what it would be.
Of solution is greater.
Yeah, than what it would be as stated by the Raoult law.
Okay. Okay,
Yeah.
thank you. Let's also have her. The one who's having her.
Teacher, there is a slight volume increase when mixing the components.
There's slight what?
There is a slight volume increase when mixing the components.
Slight volume increase of what?
On mixing the components.
On mixing the components. Okay, Erodi Savior, thank you. Thank you, ha. I don't know whether the name is LD Savior. Yes, LD Savior. LD Savior. LD Savior. Okay, 007.
Yes.
Yes, please. Now, for you, give us some examples of solutions that deviate positively.
The examples we have water and ethanol.
Water and ethanol.
Ethanol. Yes.
Which other one?
We have water and propanol.
Water and propanol. Very good. Now leave your microphone on and then you can move on together. So we see that some of the characteristics, like you have already shared with us, that there is higher vapor pressure than the ideal solution. Then number two, there are weaker intermolecular forces. Then number three, molecules escape easily into the vapor phase. Then we see there a lower boiling point. Then mixing is usually endothermic. Like someone told us that heat is absorbed, so usually endothermic, good. Then they may form a minimal boiling azeotrope. They may form a minimal boiling of azeotrope, and I believe we shall be able to discuss an azeotrope very well in our next session as we come to the end of Equilibria 2. And we are going to generate a number of scenario-based items to see whether we can attempt a number of them using the knowledge that we are getting in today's session. Examples, we have like they have already shared with us ethane and water, propane and water, ethane and methyl benzene. All these are some of the examples of solutions which show a positive deviation from the ideal behavior. Now, how does a vapor pressure composition diagram of a liquid mixture which deviates positively from Law's law look like? How does it look like? We have already seen the characteristics. So how it looks like, the characteristics are already here. So the vapor pressure, there is a higher vapor what? Pressure than the normal for the ideal, because we saw that for ideal, it is a straight. But when you see on the other one, it will be deviating positively and will be higher. Look at that. From what we have already discussed, from the characteristics, from what positive deviation is, I believe we can be able to link up with the two. Maybe one thing we need to look first put down is where the vapor phase is. So here we have the vapor phase down here, and then up this side, that's why we have the liquid what? The liquid D phase. Let's put them there. So if we are to look at this, we are still considering component A and component B, but it's not a must to use component A and B. This A can be Q, the other one can be P. So it depends on how you label your work. When you look at these two, which one is higher than the other? Anyone whose microphone is on? Are they on the same level or one is higher than the other?
Component A is higher than component B.
Component A is higher than component B. Maybe, to avoid confusion, maybe I redraw it here so that it is very clear. So, in your observation, A is higher than, yeah?
Yes.
So, meaning P, not A, if it is higher, we can have this one a little bit below and we put it here. Now, Meaning at this point, this is mole fraction down here, the mole fraction. And at this point, the mole fraction of A is equal to 1. And then at this point where it is starting from, the mole fraction of A is equal to 0. So it increases as you come this side. And of course, at this point, the one for B is also 0. At this point, the one for B is equal to 1. I believe we know that now. Yeah?
Yes.
Okay. Now, normally, if it was low slow, this one could be like this. This one could be like that. I'm putting it dotted. Why? Because this is not the original. This is what we expected. This is what we expected. This is what we expected. And then the total vapor pressure could be very straight there, like that. This is our expectation that we had. But what is happening because of the deviation from the ideal, because this is the ideal behavior, this is, maybe you can say that this is the ideal condition. Yeah? But because of the deviation, it is deviating it positively from it. So it is, the vapor pressure is above the normal. So the original one now is above. Is above. Are you seeing that?
Yes.
Even for A, you'll find out it is what also above the normal. Even this one, you find it is also above the normal, which will be like that. So this one becomes PB. This one is PA. This is our vapor phase. Maybe if I can change, I don't want to confuse. This is our vapor phase. And then this side is where we have the liquid phase. Okay. I don't know whether we still need anything else apart from what we have already seen there. The liquid phase, we have it. The vapor phase, we have it. So up here, this is where we have the P total, which is equal to PA plus PB. PA plus PB. Yeah, so I think that one is very clear. Unless someone has a question. If you have a question, you can raise up the hand. And those who are moving with in the chat, please let me know. So after you pardon for me the previous question of calculating vapor phase. Okay. Okay. Any question? Those who are on, can I see hands up if you have any inquiry on the positive deviation, or we can move on? Yes, Brian? Oh,
Yes,
very
Master.
good. Someone saying good to go. Yes, please.
Master.
Good
afternoon.
Good afternoon.
Master, my network wasn't stable and I'm enjoying the move. So I'm requesting to pardon me the first two previous slides I screenshot.
Just want to screenshot.
Yes.
Okay. Leave your microphone on and let me know whether you have been helped. That is the first slide. Are you done? You're done?
Yes. Yes, Master.
Okay. Then positive deviation. I believe those are the ones you missed.
Yes.
Okay, thank you. Can I move on now?
Yes.
Okay, thank you. Now that you have seen how we have come up to this level in drawing our diagram, meaning if they have given you the values, these values, if you have them, you can be able to draw your diagram the way we have done it right here. And one everything that we have discussed on the previous slide, or looking at the characteristics, looking at what they are the ones which we have been able to explain. So we are just looking at the deviation from Daud's law, and they will see the blue lines are showing how it is deviating from this red. It was supposed to be straight, but because of the deviation, we see it is coming above. Lydia, you'll be the last person who go to the negative deviation. Yes, Lydia?
Teacher, thank you.
Okay,
Teacher,
you have got it.
no, I would like to know when it
Mm.
comes to examination,
Yes.
are they always going to give us the various plot, or we should memorize that one?
No, if they don't give you the values and they want you to show the phase diagram, it's not a must to memorize that A has to be this side, B has to be on the other side. No. What you need to put in mind is understanding initially what is the mole fraction. When mole fraction of A is 0, you call our P total. Our P total, where we have P naught B minus P naught A, mole fraction of B plus P naught A. If you have this, when B is 0, meaning we are here. When B is 0, the constant is P naught A, meaning P naught A will be up. Are you seeing that? So when you get that into our mind very well, when you're drawing, you not need to, because when they tell you, but in a question, most probably it has to be given that for the one for A is this value, the one for B is the other value, then you can be able to draw it very well. And they get to know whether it is deviating positively or whether it is deviating negatively. That one to be there. We shall be able to bring those questions in our next lesson so that we can see how it can be set. But understanding the concept is very important.
Yeah, thank you.
Okay, welcome. Now, I see Malaika. Malaika, now that you let us look at Angel and then we end.
Thank you, Master. My question is, like, why is it always that the partial pressures of air are greater than those ones of B?
Oh, no, it's not. No, it's not a must. Okay, you wait and see our next diagram. Next diagram, we're not going to be having A or B. Next diagram, we're going to use P and Q. You get? This is just a demonstration, but if it is a question, I'm going to give you even a practice question where you're going to practice, yeah? And you shall be able to see that it's not always a must to be A or B. Now, leave your microphone on, Malaika. Are you there?
Yes.
Read for Lance. What is that?
Negative deviation.
Negative deviation. If you know positive deviation, negative deviation becomes a walkover because it is just opposite of positive. Read for us that.
Negative deviation occurs when a solution shows a lower vapor pressure than predicted by Rauty's law.
Okay, good.
This happens because the intermolecular forces between unlike molecules of A and B are stronger than those between molecules of A and molecules of B to B.
Do you think you can explain for us how this happened? Why? Why is it that intermolecular force of attraction of unlike molecules are stronger than those? Or why is it that it shows a lower vapor pressure than the predicted one? They have already given us the reason why for this, but we need more explanation to understand this deeper. Why these ones are stronger than those ones of the like molecules. And the expression is here. We are not going to take much time on that, but you can read for us that explanation.
The explanation is saying that when two liquids are mixed, strong attractions develop between unlike molecules. Molecules cannot escape easily into the vapor phase.
Hey, first wait. The reason why they cannot escape easily is because there is a strong attraction. You get?
Yes.
So due to this strong attraction which develops between the unlike molecules, that's why they cannot easily escape.
Escape to the vapor phase.
Continue.
Vapor pressure decreases below the ideal value.
Below the ideal? Yes.
Ideal value. As a result, the solution boils less easily. Boiling point increases.
I believe now you can even draw that diagram. Isn't it true?
Yes.
Yeah. So in this case, before we draw that diagram, maybe let's first look at these characteristics, examples, and then we can draw the diagram. And you can just read for us these characteristics since they are just opposite of the positive deviation. So let's see, read for us a little bit faster.
Characteristics of negative deviation. There is a lower vapor pressure than the ideal solution.
Good.
Strong intermolecular forces between unlike molecules.
Good.
Reduced escaping tendency of the molecules.
Good.
Higher boiling point. Mixing is usually exothermic.
Exothermic means what?
Exothermic means like releasing heat to the environment.
There is release of heat, okay?
Then what is that one?
This one.
No, the upper one. Is it enthalpy changing?
No, the enthalpy change, yes, the heat change of the mixture is less than zero. So like there is release. You get?
Release of heat.
Yeah, release of heat. So the final product is less than the initial. So that's why you see it is less. Yeah.
And then the sink may form a maximum boiling azeotrope.
May form a maximum boiling azeotrope. Now, the azeotrope, this one will come in when we go to composition diagrams for boiling points. And like I said, that will be in our next lesson because we can't finish all these things in one lesson, yeah? But an isotrope will come in when we're looking at the boiling point composition diagram. So this one, these characteristics, they have given us the characteristics which are showing us for general negative deviation. Yeah, so when we reach on the boiling point composition diagram, we shall be able to see an azeotrope. Now, examples, we have them there for negative deviation. And I know most of you, it's possible that you had already given us this, the hydrochloric acid and water. We have like methanoic acid. There's someone who had put methanoic acid and water. We have sulfuric acid and water, nitric acid and water, acetone and chloroform. So these are some of the examples of solutions. When mixed together, they form, they show us they deviate negatively from the ideal behavior. So our work now is to see the diagram, composition diagram for a negative deviation, for negative deviation. And what you're going to be seeing in the diagram is still a representation of these characteristics. So it will still be the same. Unless someone has a question. Malaika, have a question or Asim?
I'm requesting like you go back the previous slide so that I could screenshot them.
Asim, you can ask as they screenshot this.
Teacher, we are talking about the intermolecular forces being stronger and being weaker in different deviations. So I'd like to ask about the negative deviation. Isn't that the forces, the tendencies of attractions that bring about the stronger forces of attraction between these molecules?
I've not heard very well. Are there what?
I'd like to know the forces or what brings about the tendency of strong attractions between the molecules in this negative deviation.
Or what causes the strong attraction?
Wouldn't that be? Yes, teacher.
Won't there be what?
I think there would be some forces kind of bonding or others that may bring about this strong attraction. So I would like to get more
No,
information.
now, I believe you have seen the examples of substances. You get?
Yes, yes,
And
teacher.
every substance, you'll find out that it has different composition. Now, those substances which are having that particular composition, and when you mix them together, they develop that strong attraction. Now, the attraction is between these particles, the molecules within these substances, substance A and substance B. So it depends on which molecules are present in that substance. That's why you see the examples of solution that deviate negatively and positively are different, meaning the molecules making up those substances are also what? Different. Now, for negative deviation, those substances which have this kind of deviation, their molecules, they develop that strong what? Attraction. The issue is about the particles present. It's like in real life, if we have a boy and a girl and a boy, the attraction, a strong attraction will be where? Between a boy
The
and
girl, a
girl.
girl.
Why? Because of the different charges. Because one is a metal, the other one is a non-metal. Did you know that girls are non-metals?
Teacher, I didn't know.
Hey, okay. So boys are metals because you call the boys, a metal has a property of loss of electrons. While the
Yes, teacher.
non-metal, they have those properties of gaining what? Electrons. So if you find that in a room there is a boy and a girl, or boys and girls, the attraction, there will be a strong what? Attraction. The tendency of these people moving out will be low compared to when there are only girls in the room. The tendency of these ones escaping in the room will be what? High, moving outside. I believe you get the scenario. Yeah? So it depends on
Yes,
the
teacher.
molecules present in that particular substance.
Okay. Thank you, teacher.
Okay, welcome. Now let's look at this diagram and then we can go to, for this diagram, we are just going to draw it from scratch. Only that I don't have a ruler here, but it's better you use a ruler. But let me try to use mine here and we see. So use look at that. It is vapor pressure composition diagram of liquid mixture which deviates negatively from Laut's law. Now, it is just the opposite of what we had. So what I'm going to do, let me see whether I can draw it very well. Good. It is straight. Let me see also here. Hey, where are you starting from? Here. Good. Then here. Nice. So I'm going to use, so here we have composition. Down here we have composition. But do you know that the composition, we can use percentage composition, we can use percentage composition, or we can use the mole fraction. Did you know that?
Yes, teacher.
So if you use percentage composition, here we can say 100% of substance X, meaning here we have 100% of substance Y. So this time around we're using Y. Now, if this is Y, meaning at this point the mole fraction of Y is equal to 1, meaning if its mole fraction is 1, meaning at this point we are going to be having the partial pressure of Y. Now let's take it that this one is higher and then this one is what? Lower. So here we shall be having the partial pressure of X. Now normally it could have been, if it obeys Lord's law, we could be having, but don't forget that this is this side. It is vapor pressure. So it could be very straight line, but because it's not the original, we are going to have dotted. Even here, it could have been like this. It could have been like that. Okay. Then the total vapor pressure could have been also very straight like that. And you recall this is the representation of ideal condition. Ideal condition. Up here, that's why we have the liquid phase. And then down here is where we have the vapor phase. So since we have our vapor phase there, what is remaining, I'm going to use another color to represent the original one that we are looking for this deviation. Now, we said for negative deviation, the vapor pressure is lower. So meaning instead of going up this time around, it is going to be down like this. Then here it will also be down. Down, 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 down. And also here it will be down. Now, when it goes down, meaning this is our partial vapor pressure of Y. This is our partial pressure of X. And then here we have P total. Things are going to become very many. They disturb us. Let's use maybe black. So this one becomes P total, which is equal to Px plus Py. Is that clear now?
Yes, teacher.
Do you know that at that point we are done drawing the vapor pressure composition diagram of negative deviation? Anyone with a question? Me, I'm done. That is it. Maybe what I've changed here is to use composition, percentage composition instead of mole fraction. And I said all those two can work. You can use mole fraction or you can use percentage composition. Unless someone has a question. You have a question?
I have a question.
Yes.
My question
yes, you ask.
I'm asking, like, of these two partial pressures of X and Y, like at first, which one do I like on the percentage composition, their percentage composition? So in the question, they told me that the percentage composition of this of X is 1/100.
No, you see, percentage composition, it's like our mole fraction of Y is 1. Our mole fraction of X here, of X is 1. You get? So instead of using, because if it is 1, which means its percentage is 100.
Yes.
Like it's a, then if it is 0.8, its percentage will be at 80%. If it is at 0. So it's like converting mole fraction into percent. So it is the same case like I've been doing.
I'm getting that, but the confusion is like still with that. Like now I'm considering if the partial pressures of X are starting from this side as 0, going to that side of Y up to when I reach 1.
Yes.
Like my confusion is about those partial pressures and like when do I have 1 this side and why do I have the 0 this side of X and why?
So when do you have 100% this side? When do you have 100% this side?
Yes, and then the other, like, why is the partial pressures of Y like up, like higher than those ones of X?
No. Now, keep your microphone on.
When
the
one
for Y, you recall this is Y. Why we don't know what Y is. Y is any substance which they have not yet told us.
Yes,
even
master.
X is any substance which they have not told us. But for us, we are assuming that Y is having a higher vapor pressure than X. But for you, like even this diagram, the way you're seeing it here,
I can also decide.
You can decide to have. Yes, you can even decide to draw this diagram like this: P not X, and here we have P not Y, and then this one will be like that. And then this one could be coming down here, coming down here. Meaning at this point we have 100% Y. Here we have 100% X. This is our composition.
Okay, Master.
Then,
Thank you, sir.
yeah, have you seen that?
Yes.
Yeah, so I think here it becomes very clear. So here is just our demonstration. So you can use X for any, you can use even A, you can use B. That is when they are not clear. But if in the question it is very clear, then you can be able to answer. Look at this question, your assignment. Your assignment, take a screenshot. I may not give you the answer now, but take a screenshot. We end here, and you give me your answers in that group, or you inbox them. You can inbox them. Write the question very well. Answer part A, and you answer part B. Maybe to read for you as you take screenshot. They're saying that calculate the composition of A. Now this time around they want composition of A and B in the liquid mixture AB, which boils at 90 degrees Celsius and 760 millimeter per mercury. The saturated vapor pressures of A and B are 948 and 369 millimeters of mercury, respectively. After that, calculate the composition of vapor above the liquid mixture in A when it boils. So that is the question. Take a screenshot, maybe if I can give you the answers so that you can prove yourself whether you're right. Sorry. The answers for this, note them down so that you can prove yourself whether you're right. The composition, that is the mole fraction of A and mole fraction of B, but in percent. Mole fraction of A is 84.2%, and then down for B is 15.8%. So try it out and see whether you get that answer. If you don't get it, please make sure you inbox, and then I can be able to help you out. But we shall also start from there even next time. Then for
Excuse
part
me.
B, yes.
Teacher, I have a question.
Yes.
What if I'm given the units when they're different? For example, they give me in mmHg and then they give me also in Pascals. Am I supposed to change them to one unit?
Very much. Why? Because you can't add things which are not in the same units. Are you seeing that?
Which one? Yes, teacher.
So we have to make sure that we convert to the same units. So you need to know how many, 1 Pascal is equivalent to how many millimeter of mercury. And I believe those conversions, you have them.
Yes, teacher.
Yeah. Now look at this. Are you seeing the answers for part B? Answers for part B, they are here. Answers for part A, they are here. Just going back to the chat. Someone is saying, someone to add me in the group. I've given you the link. Click on that link. Subscribe to it. You, after subscribing, you'll be directed to also the group. You'll be able to join. So please, those who are on the chat, make sure you also share with your friends the link so that you always check on the work which is already there. These topics have been already explained in the chat, in the playlist on that link I've given you. But make sure you subscribe, then you also share with your friends who are not here, so that they can also always benefit from whatever we discuss. Unless someone has a question, we asked Chemali, unmute. You tell me, then we can close from here.
Good evening, sir.
Good evening.
Sir, like I have a request. Could we please arrange for something to do with practicals, maybe also another day?
Okay. Practicals, meaning we have only next week. If you have only next week, then we shall organize, and then we shall organize with the coordinator, and we say that we can have a day, maybe before lunch, one of the days next week.
Thank you, sir.
But that one we can inquire from the coordinator whether we can have fix a day, because we have only next week, I believe.
Okay.
Otherwise, I want to appreciate each and everyone for participating and for being part of this session. We have come to the end of our session. This video will be also shared. Like I have shared the link in the chat. Let's make sure we go there, we subscribe. When you click on the link, you'll be directed to the subscription button, and then you can be able to subscribe as fast as you can. Otherwise, if you have any issue, you can use that number on that screen, and then can be able to add you in the holistic senior 6 group. We shall give you the link. You can also inbox on that. Otherwise, have a blessed time. And let me request one person to lead us in the closing prayer. Who can lead us in the closing prayer?
Shami.
Okay, lead us.
Okay, let's sum ourselves for prayer. Almighty King of Kings, Lord of Lords, we thank you for this lesson. We thank you for the blessing you've bestowed upon us, upon our parents' finances to cater for our online lessons. Lord God, Father, we do not get tired of thanking you, and we are here also today to say we are really grateful, Almighty God. We thank you for our teacher, for we've had a lesson that we may want to get each and every day, mighty Father, because it is full of free expressions, mighty Father. We thank you, Lord, for this is your grace. We worship you, we give you glory. Grant us journey mercies from where we are learning from, and grant us great memory, Lord God, Father, and insight to know whatever they are teaching us for our USC examinations, mighty Father. For the glory of your name, we do pray and believe. Amen.
Amen. Thank you very much. Let's meet next week in the next session.